believe in yourself, for that's the place to start. And I say, hey, hey, what a wonderful kind of day, if we can learn to work.
Okay, everyone. So this is a challenge to myself, right? Can I define what quantum is in 5 minutes or less while relating it to the classical world? And I'm going to try it real fast, right? So the first question is, what ingredients do we need from the classical world and to understand why it's different from the quantum world? Well, the two things we need um, come from Newtonian and electromagnetism, right? So in the Newtonian picture, particles are like the main thing. And we say Newtonian physics is a causal, deterministic theory based on the principle that all I need to know in order to determine all physical phenomenon precisely is I need to know its the particle's initial position and its momentum. That's it. If you know those two things, you can uniquely and precisely determine all physical phenomenon associated with the particle in a classical sense. Electromagnetism, on the other hand, is also a causal and deterministic theory, but in a different way. Notice in the Newtonian picture, there was a finite amount of things I needed to know. In the electromagnetism picture, on the other hand, we actually have to break down the electromagnetic field. And what that means is, in order to see that electromagnetism is causal and deterministic, we need to know the direction of the electric field, the direction of the magnetic field at all points at a given time. And that might seem radical, right? So that's almost like an infinite amount of information I need to know about something. But it's a mathematical framework. And if you apply the mathematical framework correctly, which, hey, I'm recording on something that applies these principles, right? You see that, oh, cool. I can actually uniquely determine the distribution of the electromagnetic field based off of these principles, right? And so that is a causal deterministic theory. And so it's very interesting, right? So let's really just break down quickly what does causality and determinism mean? They're very subtly related, but they're hugely different. So causality means simply that if I know the information at a certain time of a state, so Newtonian physics, this would be I need to know the position and I need to know which direction and how fast it's going. If I know those two things, that's the information of a state, then there is at a different time I can measure that state and I will get some unique information about it. That's it. There is no mechanism to relate it. Okay, that's all causality means. Determinism, on the other hand, is the concept that, okay, let's go back to the Newtonian picture real fast. I know the position and I know how fast and which direction the particle is moving. Then I can precisely determine everything associated with that particle real time. Okay? That's pretty damn important. That's pretty damn cool, in my opinion, right? Very confusing, but pretty damn cool. So we say in this classical world, they're deterministic because of that mathematical property, essentially. And it's mathematical in my perspective, right? Because it might work on Earth, but like as we see as we go further on in physics, you go super small, you go super big. Um, guess what? Breaks down. So it's a pretty cool ideal that works most of the time, right? And so now, in my opinion, right, quantum theory is really just marrying those two ideas together. In the classical world, it's not as married as we would like to think, you know. Um, in one hand, we have a distribution of fields, and we need to know have infinite precision and a continuum. One of my favorite things to think about is like given a source, blasting off a radio wave, right? You can determine in a continuous fashion how that radio wave is going to break down, right? Um, it's deterministic, it's causal, but it's very different in the quantum world. So, what happens in the quantum world is we start to notice this phenomenon, right? We notice this phenomenon that, like, for example, if I shine electrons through a crystal, right? and you do, let's say you just do one at a time. So you throw one electron through this crystal, it goes through the crystal, right? Um, and it's for physicists, it's important we emphasize crystals here. For the layman, for those watching the video, it doesn't really matter too much, right? The reason why you want to use crystals is because crystals have a structure that's very rigid to them, and it's like a lattice structure. So it's very easy to do experiments through them because they're very it's because of that lattice structure. I'll just leave it there. It's because of the lattice structure. I don't want to do a video on that field because I'm not very good at solid state physics. So I'll leave the crystal structures and the D-Root models and all that stuff to the real solid state physicists. So for now, I'm just gonna take their idea and apply it here. So, anyways, so we throw an electron through this crystal, and we have a detector, we have a screen can show us where it lands, right? And so at first we go, lands there. Okay, weird. Let's do another one. Wait, it landed somewhere else. Huh. That's weird. You throw another one out there. It landed somewhere else. And so what you start to notice that the distribution on our screen is almost as if this particle-like thing that had that particle-like property, it's going one at a time and it's acting like a particle. It's going here, it's going here, it's going here. What you start to see is that the distribution on the screen is almost as if the electrons as a collective behave as a wave. And so that is, in essence, what quantum theory is about. The individual events are truly random. You cannot predict them, right? You truly cannot predict what is going to happen in an individual event in a quantum scenario unless you do some certain things. But once you, like, for example, let's say I'm going to make sure it shoots to this one position. Cool. Well, then you break down the wave-like properties that you see. You break down the quantumness of it all, right? So in the real world, in random experiments, right, what we find out from the quantum world is it's causal, right? The state is uniquely determined initially, and it's uniquely determined later on, but there is no way to predict the individual physical phenomenon associated with each individual particle. It's not deterministic. It's causal, right? Because all causal is, at its bare essence, is if I know the state at this time, then I can use it's uniquely determined another time. No linking between them. That's it. It's just the same state that's changed. It's evolved somehow, right? Same thing happens here. Now, the cool thing about quantum mechanics, though, or I guess quantum theory in general, is even though I can't predict, I cannot predict individual events. They're truly random. But what can I predict? Think about the screen. I can predict that distribution. That is, in essence, what quantum mechanics is about. The individual events do not matter. But that distribution, I can predict that every single time. And so to me, what I think is really cool about this, because it's not just a physical phenomenon we're talking about, right? This idea transcends just this physical logic we're thinking about, right? To me, what I think the really cool thing about applying this logic, like truly understand that concept is, well, you can apply it to society as a whole, right? Think about it for a second, right? You take an individual within a society, the individual's action within a group really does not matter all too much within reason. Within reason. You can't predict it. I think that's a better way. You can't predict the individual's actions within a group. But what have we learned? The unfortunate reality is, and a lot of times you can predict the actions of the group as a whole. You may not be able to predict, Jimmy, Jorge, Salima, Peter. You may not be able to predict their individual actions, but as a group, we do a pretty good job at predicting what's going to happen for them. And so I think it's a pretty cool link between, physics and society as a whole. And so the main takeaway is why do we need quantum? Well, because quantum is the act or the art of studying systems that individual events cannot be predicted. But the you can predict the effect of them as a group. So individual electrons don't really matter, right? And a very cool phenomenon also that comes from this concept is the concept of indistinguishable particles. Sounds pretty fancy, but essentially that's exactly what it means. You can't ever say this is electron one and this is electron two. Because if you can say this is electron one and this is electron two, you would be able to have a deterministic way to look at its history. And so I'm going to leave this here because it's supposed to be a 5 minute video, not more than 10 minutes. But that'll be for the next concept, and I explain indistinguishable particles in under 10 minutes. Um, is that you cannot determine, you cannot follow individual particles at all. But I digress. Hopefully that makes sense. This is just a quick 10-minute video on why quantum. So hopefully you enjoy.